Hello, everyone. Welcome to our TJ Senior Research Project on Social Inflatable Robot. My name is Raghav.
My name is Ram.
My name is Chris.
My name is Jason.
In the description of this video, we'll include 2 links to demonstrations of our robot. To give you an introduction for our project, we looked at a lot of robots, and many of them have an industrial perspective in mind. And they're made of rigid materials like metal, which aren't as user-friendly for consumer spaces like hospitals and senior living spaces. Inspired by the robot Baymax from Big Hero 6, we decided we wanted to build a social robot that has a soft exterior that can easily work in any consumer-oriented space.
So we envisioned to create a robot just like Baymax, as you saw in the previous slide, that was both huggable and human-like. And we had 3 main objectives to actually achieve this. First, the robot needed to be portable in that it needed to fit in a 1 foot by 1 foot by 1 foot box. 2, it needed to be inflatable so that it could be inflated with an ordinary air pump that you could find in your house. And 3, it needed to be able to be communicate in a human-like manner.
So now that you have a idea of our project proposal, we'll move on to our mechanical and electrical systems. So for the mechanical design process, our goal was to create a airtight enclosure that could house the electronics, and we wanted it to just be able to hold the electronics without falling apart. So we started this process by CADing and creating a wooden model of the robot chassis. And then after this, we scaled the initial CAD after we got the electronic components to make sure that we could fit all the electronic components inside, such as the speaker, Arduino, Raspberry Pi, and so on. And after we scaled it, we 3D printed and laser cut the chassis.
Similarly to the base, we also created a lid for the chassis using CAD to first model the lid and then 3D printing and laser cutting out parts for it and then hot gluing the parts together to create the lid. Attached to the lid, we also sealed the plastic inflatable on it. The first iteration of the inflatable was created using plastic sheets and taping them together to resemble a dome on the top and a cylinder on the bottom. Future iterations of this design focused on decreasing the radius of which the bottom of the dome and top of the cylinder were connected to create a more head-like structure and therefore a more human-like structure. We also used an iron to heat the sheets together instead of taping them.
Now I'll give you an overview of our electronics design. The overall goal of the electronics system was to create robust hardware that integrates with the software. We used a Raspberry Pi to host our wireless control for the motors and to also host the chatbot. Additionally, we used Arduino as a PWM driver, which is used to control the motors. So here's an overview of what the system looks like as a whole. You can see the Arduino controls the motor, and we have an external power supply to power the motor. These motors are powered indirectly using the Raspberry Pi over USB, and the Raspberry Pi houses the mic and speaker, which is in charge of the chatbot. And finally, this whole system is wirelessly connected to a host computer via a Pi socket, and this operates over a hotspot network. Now I'll turn it over to Ram, who will talk about the software.
About the control system structure, we have the client-server connection between the Raspberry Pi, which is the client, and the computer, which is the server. And the Raspberry Pi basically controlled all the motors and also the chatbot. And the connection was created using Python sockets. So the Raspberry Pi connects using something called a transmission control protocol using IP and ports. And you can see in the bottom left, there's a picture of a successful connection. And in the bottom right, you see the computer and the Raspberry Pi that we used for our project. So now specifically inside the Raspberry Pi, we had a lot of threads to actually simultaneously run all of our motor control and chatbot features. So commands would basically be transmitted from the computer to the Raspberry Pi. And then once the Raspberry Pi received the commands, it would then be inserted into a priority queue where the commands would be prioritized depending on how important it would be. So if it was motor control, that would be more important than simply activating the chatbot. And as you can see in the right, we have the 4 threads I've talked about earlier, like the receiving and transmitting the commands, also checking if the commands were valid, and also executing all the commands. So here are 2 diagrams of first the client and how the threads functioned. So each box would be a thread, and then also a server diagram where we have the telemetry receive and telemetry transmit threads.
Now I'll give you a brief overview of the chatbot system, which is one of the commands that a user could take on the control system. So to create a chatbot, initially we tried creating our own ML network trained on a Kaggle dataset, but unfortunately this Kaggle dataset was relatively small and didn't provide enough data for our chatbot to accurately respond to a user's requests. So eventually we moved to the OpenAI DaVinci 3 model, which is the same model used on ChatGPT. This model is trained on a much larger data set and allowed us to get more accurate results for our users. So to go over the overall process of how this works, first we take speech from the user, which is obtained from the microphone, and we feed it through the speech recognition library, which runs Google's speech recognition model to change the speech into a string. And then we take the string and we pass it through an API call to the DaVinci 3 model using the OpenAI library. And then as we pass it through this library or this API call, we get a model output. And this model output is finally translated into a spoken speech output so that the user can hear what the model is saying in response to their speech from the start of this process. And this basically creates a conversational experience for our end user. In terms of the feasibility of this system, it's very easy to deploy as it's simply an API-based system. It doesn't require us to put any ML model directly on the Raspberry Pi and uses a web interface to access API calls. It's also easy for any user to use, as all they have to do is register an OpenAI account with a personal and organization key and enter it into our software, and then they're able to use all the features of our robot. And finally, in terms of pricing, it's quite economical. After all these months of testing, we only ended up spending $2.43 in terms of API calls, and about 30 to 50,000 tokens is equivalent to $1. So it's relatively cheap to use.
So now we'll move on to project testing, and we use an iterative design process to build this robot. So this is demonstrated on the images on the right. You can see in the top image, with the old wheels and motor mounts, we used 3D printed motor mounts. We also used rubber wheels, and the motors that we used were RC motors. However, in this design, the RC motors did not have enough torque to properly move the robot, and also the rubber wheels had a lot of trouble when the robot was trying to turn. So on the bottom right, you can see the revised robot. It featured Vex motors, which were strong enough to make the robot move, and the Omni wheels also experienced no trouble turning. And we also dropped the chassis a couple times to make sure that it was reliable in case someone dropped it.
So we also monitored the code and electronics for any bugs, or if there was anything like any problems that we needed to fix. And we also had people outside of our lab like test our robot to improve like the usability and also make the code more efficient.
Overall, our project has met the objectives we had set for it. It was capable of holding conversation with many different people. Specifically in the video, you can see it speaking with a user. Our robot was also capable of inflating and deflating. it was able to receive and execute multiple different movement commands from a remote device, and it fit within the size constraint we set for it of a 1 by 1 by 1 box, making it portable and easy to carry around. And thanks to this small and simple design we had for it, it is capable of being scaled and customized to fit specific environments. Unfortunately, due to time constraints, we weren't able to implement all the ideas we had for it, as Raghav will talk about in the next slide.
As Jason said, we're pretty happy with what we were able to accomplish in the given time frame, but we do have some recommendations of where future students can take this project if they decide to pursue the area of social robotics. Some ideas include autonomous movement so that the robot can move in an environment of a user on its own. We'd also like to have a graphical user interface, as this will allow the end user to more easily interact with the robot instead of using a terminal. We'd also like an overall more human structure for our robot instead of the current inflatable, so that the robot is more like a human and more trustable and more usable in any environment. We'd also like automatic inflation so that the robot can create its structure on its own instead of us having to inflate it with a pump manually. And finally, we'd like to have a natural sounding voice so that the robot sounds like a human and not like a robot, so that it's more user friendly. And we thank you for listening and can take any questions in the comments.